quadrilaterals are simply four-sided diagrams, four-sided figures. Okay, so there is no specific property out of any random quadrilateral. Okay, however, there are properties for special quadrilaterals. Okay, for example, your rectangle, your squares, your kite shapes and all that. Okay, we will look at that later on. So looking at just a quadrilateral itself, we must know how naming actually happens. So usually, how we name a quadrilateral, we will start with any one of the vertex. So all these corners are what we call a vertex. Okay, so just to spell it. Okay, so vertex is singular, vertices is actually plural. Okay, so let's say if I start from A, okay, name this quadrilateral. Usually we go in a clockwise or anti-clockwise manner. So you can call it quadrilateral A, B, C, D, or you can call it A, B, C, B. You need not always start at A, you can start at C also. So C, D, A, B, or C, B, A, D. Okay, so long as you stick with going in a clockwise or anti-clockwise manner. Okay, what you cannot do in naming is that you want to go B, D, C, A. Okay, you cannot go all over the place, right? Because that will be very confusing. So whenever they name a quadrilateral to you, okay, you can draw it in a clockwise or anti-clockwise manner. Okay, clockwise is this way, anti-clockwise the other way. So a point to note. minus 86 degrees. 118 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 minus 86 d integral sum of quadrilaterals. Now, you see the Venn diagram at the bottom. I'll come back to it later on. Okay, I want us to scroll to, not scroll, but turn to this page. Okay, this segment may be a little bit dry. Okay, so just bear with me for a moment. Okay, I want to run through with you all the different properties of different special quadrilaterals. Okay, we have nearly six different special quadrilaterals. You may want to go onto this link, okay, if you want to go and explore and see the different quadrilaterals. Okay, however, some of them we are already familiar with it. So for example, in our rectangle, okay, when talking about parallel sides, how many pairs of parallel sides are there? How many parallel sides are there in a rectangle? Two, right? Okay, so there are two pairs of parallel sides. Okay, opposite sides are equal in length. Okay, so for example, AD is equals to BC, CD equals to AB. Likewise, we also know that interior angles, okay, all four of them are right angles. And about the diagonals, okay, the diagonals are actually equal in length. And the diagonals bisect each other. So what does bisect actually mean? Okay, bisect means that you divide something into two equal parts. So diagonal refers to this line over here. So for example, the diagonal AC, it will cut the other diagonal into two equal parts. So this and this length are equal. Okay. Likewise, this diagonal over here will also cut this into two equal parts, such that this length AE is equals to the length CE. Okay. But because both diagonals are equal in length, we are also able to conclude that, okay, all the smaller parts are equal in length. Right? This is a helpful property because what kind of triangles are we able to see from this rectangle now? We are able to see isosceles triangle. Okay, and then later on we can apply isosceles triangle property in order to find the smaller angles within the triangle. Then we have our square. Okay, so in our square we are also aware that there are two pairs of parallel sides, and very importantly, how is it different from a rectangle? How is a square different from a rectangle? All the sides are equal, right? So all four sides are equal in length. Okay, your interior angles, all four angles are also right angles. Okay, and then we also see that the two diagonals are equal in length and the diagonals bisect each other. Okay, but something that distinguishes it apart from a rectangle is that for a square, the diagonals bisect each other at right angles. So there is that 90-degree over here. Very different from a rectangle because very clearly from this diagram itself, I can already tell that they are not 90 degrees. Okay, so the two things that distinguishes between a square and a rectangle is firstly, okay, your sides that are equal, whether they're equal or not. Okay, and then also this part of diagonals bisecting each other at right angles. Okay. Questions? Yeah, question. Sorry? You don't understand which one? Bisect each other at right angles. It means that this diagonal, okay, it passes through the other diagonal, okay, and then when it passes through, this angle over here, I can measure it to be 90 degrees. It's only for a square. Okay? Our rectangles, they don't have that. From the diagram, I can tell this is not 90 degrees. Okay? Right? Because this diagram is very, very different. Right? That I have printed off. Okay? So, I can still have the equal sides. Okay? So, they are still equal over here because they bisect each other and they are equal in length. Okay. Any other questions? Before I move on to the next one? Yeah? Let me just try to merge these two equations together. Okay. Next we have our parallelogram and rovers. Try to scroll this out a little. So in a parallelogram, okay, they are similar to our rectangles as well as they are similar to our squares. They have two pairs of parallel sides as well. Okay, and then opposite sides are actually equal in length, meaning to say DC is equals to AB, AB equals to BC. Okay. So at this juncture, do we say that a square and a rectangle is also a parallelogram? Is a square and a rectangle also a parallelogram? Okay, so square and rectangles, they are parallelograms itself. Parallelograms is a much general term, okay, whereas square and rectangles, they are much more specific. Okay, what is something that makes them specific? Firstly, have a 90-degree interior angles. Okay, because not all parallelograms need to have the interior angles to be 90 degrees. Okay, so what draws the square and rectangles apart from a rectangle is the interior angles being 90 degrees. Okay, so that's one of them. Right? Then for squares, even more specific is that all the sides are going to be equal in length. Okay, so I want us to be able to see and understand at this juncture that if I were to draw a Venn diagram, okay, we have our parallelograms, okay, followed by our rectangle, okay, and a square is even more specific, okay, because not only must they be interior angles 90 degrees, all the sides must also be equal in length. Okay, so this is how we can understand and relate, okay, the relationship between parallelograms, rectangles, and squares. Okay. Then, in a parallelogram also, our opposite angles are equal. Right? What this means is that this angle over here is equal to this angle, and this angle here is equal to this angle. So that's what we call opposite angles. Okay? Okay? Then the diagonals, they bisect each other. So this diagonal AC will cut the diagonal BD into two equal parts. Likewise, the diagonal BD will cut the other diagonal into two equal parts. Okay? Your diagonals in this case for parallelogram, they may not be equal in length. Okay? So diagonals may not be equal in length. So this one is bisect. Sorry, wait. Diagonals are equal in length. that they are equal in length. Okay, I think from the diagram itself, we can also see that this looks a little bit longer, okay, while this looks a bit shorter. Okay, so therefore the diagonals may not be equal in length. Okay, so sometimes, okay, when it comes to any of these special quadrilaterals properties, okay, having a diagram will be very helpful for you to recall what are the properties itself. Okay, now moving on to a rhombus. Okay, a rhombus, there are two pairs of parallel sides. Okay, so similar to our parallelogram. What differentiates between a rhombus and a parallelogram, okay, is that for a rhombus, all four sides are going to be equal in length. Okay, so a rhombus is even more specific, okay, than your parallelogram. They require this extra condition that all four sides are equal in length. Okay, then the interior angles, okay, are going the opposite angles, okay, will actually be equal. So in other words, this and this are equal, this and this are equal. So that is similar to our parallelogram as well. Okay. Then the diagonals, they bisect each other at right angles. So what this means is similar to a square. Okay, there will be a 90-degree angle over here. Okay, so they cut each other into two equal parts, and then after that, there is a 90-degree angle being formed. Likewise, the diagonals bisect the interior angles. Okay, so if I want to draw a relationship between our parallelograms and the rhombus, I will see that my parallelograms are on the outside. Okay, and my rhombus, okay, is over here. Right, because you need all four sides to be equal in length, okay, in order for it to be rhombus. So rhombus is a much specific, okay, subset as compared to your parallelograms. Okay, later on I will give you a fuller Venn diagram. Okay, so with this rhombus itself, okay, my next question is, where can I put my squares? My squares should lie even further inside, okay, of my rhombus. Okay, why is that so? Because not only all four sides have to be equal in length for squares, your interior angles must also be 90 degrees. Okay, so this idea, okay, about how we relate to different kinds of quadrilaterals, it layers upon one another. Okay, it adds on one after another. Right? Be more and more specific requirements. Okay. Moving on to the last one, the last two. We have our trapezium as well as our kite. So in our trapezium, there isn't much property out of it other than having only one pair of parallel sides. Okay, so CD and AB. Alright, maybe I correct myself, it is not just only one pair, but strictly speaking, it is at least one pair. Okay, so if I want to improve on these diagrams that I have over here, trapezium is at least one pair, parallelograms is two pairs, they must have two pairs. Okay, so trapeziums, okay, will be further outside of our parallelograms because parallelograms need two pairs, okay, of parallel lines. Right? Regarding its diagonals and its interior angles, okay, there isn't much property out of it. Okay, other than the fact that your parallel lines will give you interior angles, parallel lines, such that these two angles they add up to be 180, and then these two angles they add up to be 180 degrees. But of course, that is not a property, okay, for your trapezium, right? Because that is a property that applies to any parallel lines with a transversal itself. Okay, and then for our kite, okay, this is our usual conventional looking kite. A kite is such that there is at least two pairs of equal adjacent sides. That means that two sides that are side by side each other, they are going to be equal in length. So in this case, AD is equals to CD, and for the other pair, okay, they are equal in length as well. Okay. The diagonals are also such that they cut each other at right angles. Okay, so there is this 90-degree angles over here. they cut each other, they do not bisect. Okay, I want to correct this word over here. Instead of other diagonal, right? We say that the longer diagonal will bisect the interior angles. Okay, so in this case, what this means is our longer diagonal refers to this line over here. It will cut the angle here in two equal parts. It will also cut the angle here into two equal parts. Okay? Questions? Alright. Now let's go back and classify our quadrilaterals. Okay? In the notes that I printed for you, I realized after printing that I might have made a small mistake when I printed this diagram. Yours will look such that, okay, for this circle here, okay, yours has this gap that is present here. If you look at the diagram that you have, okay, not sure whether you can see that there is this gap over here. Okay, by right there shouldn't be that gap, okay, because there isn't any overlap, there isn't anything formed out of that. Okay, it should look like this. Okay, but whichever the case, doesn't matter. Okay, we just need this Venn diagram to help us draw a relationship across all, okay, our different types of quadrilaterals. Right? I want us to label, okay, the different circles or the different areas, such that this big circle here is A. Okay, this is what we call B. This is C, D, E, and F. Okay, I want you to be careful about how you indicate the arrow. For some, I'm indicating along the circumference of the circle or the oval. Okay, while the other arrows, okay, sometimes I will be pointing to some space. So this B, I'm referring to this. Okay. So just now we saw that our trapeziums was further outside, okay, than our parallelograms, than our rectangles, than our squares. Okay, so therefore this circle A over here, okay, will represent our trapeziums. Okay, because for our trapezium, there is only one pair of parallel lines. Right, so you may want to take this note, okay, somewhere around the space that's given around the diagram. Okay. Right. Then for kites itself, kites are rather unique on its own. Okay, there isn't any parallel lines. Okay, so therefore we will label this other circle. Okay, so we have two big main circles here. Okay, the one that's labeled F, that will be our kites. Okay, so I'm just writing down the key feature of the quadrilateral that we have. So trapezium, the key feature is that there must be at least one pair of parallel lines. Okay, and then for kites, there are two pairs of equal adjacent sides. Then earlier on, after trapezium, we saw that there is our parallelogram. Okay, and why is parallelogram inside? It is because, okay, other than it being a trapezium, there is also one added condition, okay, that there must be one more pair of parallel lines. Okay. Sure, is it okay, there are parallelograms. With an added condition that the interior angles are 90 degrees. Okay, so I'm layering on from one shape to the other shape. Okay, that will draw the distinction between rectangles or parallelograms or rectangles or trapeziums. Now for D and E, we see that for D itself, it is within the overlap, okay, of our two main circles of trapeziums as well as our kites. Okay, so there is this big circle here, okay, and then this big circle over here. Right, so D actually lies within it. So it must be something that is both a trapezium as well as a kite. Okay, so in case you're wondering how is it that a trapezium can also be a kite, that's very confusing, right? Okay, maybe let's go with kites first. Okay, kites, we know that there must be two pairs of equal adjacent sides. That means on a side-by-side basis they are equal, and then on a side-by-side basis they are equal. Okay, but for rhombuses, okay, sorry, I got very well drawn. Let me draw it better. For my rhombuses, do we agree that on a side-by-side basis, this side and this side are equal, right? This side and this side are equal. Okay, so a rhombus is actually a special kite because all four sides are equal in length. Okay, not only is it side-by-side equal in length, okay, all four happen to be equal also. Okay, so that's why a rhombus is a very special kite. Okay, because in our generic kite, only two of them side by side equal. Okay, but rhombus all four are equal. And then for our squares, just now we have already agreed that squares are more specific, okay, than rhombus because not only there are parallel lines, all four sides are equal in length, but they are also such that they have our 90-degree interior angles. Okay. Right? But how does square interact with our rectangles? Okay, they are actually rectangles such that all four sides are equal in length. Okay, I take a pause over here. Think whether you have any questions at this juncture. Okay, in case maybe one of your questions is, your exam asks me how to label this diagram, my answer is no. Okay, however, being able to organize, okay, all your information in such a manner will be very helpful, especially if you're going up to upper sec, okay, where we see more quadrilaterals and we need to in fact go and prove them. Okay, if I give you a shape, right, how are you going to prove that this shape is going to be one of these? Okay, so what are the conditions that will need to be satisfied? Right? So these are the things that you may encounter when you are upper sec. So at least now I introduce it to you, okay, which explains also why I told you that my set of notes, please make sure you keep it all the way until you graduate. Okay? Right. However, any last questions before we start looking at some examples? Yeah? So let's look at some examples. Actually, you can go and use the toilet for you first. Okay? Intersect just simply means that they cross one another. It is not the same meaning as bisect. Bisect, as the word suggests, bi means two, so it must cut into two equal parts. Okay? So this just cross each other. Not the same as bisect. Okay? The question also told us that angle ACB is 63 degrees. First, in part I, we want to find out what is angle BEC. Okay? So if you recall just now when we touched on rectangles, okay, we know that our diagonals are equal in length and our diagonals also bisect one another. Okay? Such that all four of these lengths are equal. And we have isosceles triangles before. Okay? So if I can see an isosceles triangle, I know that it's 63 degrees. I will know that this will also be 63 degrees as well. Okay? And therefore, it will help us in finding out what is angle BEC. Okay? It may look very simple. The problem is how do we write that all out? Okay? First, I needed to say that the diagonals bisect each other, okay, such that I can form my isosceles triangle. So I will say that in part I, BE equals to CE because diagonals are equal in length and bisect each other. Unfortunately, I do not have a short form for you. Okay, this is the best that you can do. Right, you just need that you know that diagonals are equal in length and bisect each other. Okay. Then we will see that angle CBE equals to 63 degrees because of your base angles of isosceles triangle. And finally, our angle BEC will be 180 minus 63 minus 63, which gives us 54 degrees. 126 degrees. Due to adjacent angles on the straight line. Okay, then ACD or ECD, okay, angle ECD, then wow, okay, so equals to 90 degrees minus away 63 degrees, okay, and then we will get 27 degrees, then
Goes to 100 plus 126 minus 27.
Okay. Right. We do get a final answer which is 27 degrees. Okay, but Xavier, I want you to think a little. Do you think it was necessary for us to even find out what is angle ECD? No, right? What could we have done? Okay, because we can recognize the isosceles triangle, isn't it? Okay, so this step wasn't actually necessary. So we could have shortened to find that angle CDE is 180 minus 126 divided by 2. Okay? Thank you. Okay, that's it. Yes, Trixie. Wait. Okay, let me just forward the point. Looks like the over there is on the road, okay? Okay. Yes, Z shape. Oh, okay. So she recognized that is this parallel lines because it is also a property of your rectangle, right? Okay. And then if I can find out what is this angle here, okay, which is 90 minus 63, I will also be able to find that. That's also okay as well. So let me just form up how that what's it called? That set of working will look like. Okay, so alternatively, our angle CBA is 90 degrees because it's an interior angle of rectangle. Angle ABD equals to 90 degrees minus 63, 27 degrees. Okay, and then angle CDE equals to 27 because alternate angles parallel lines. Okay, so I think that's a good set.